So I wanted to have a few words taking a step back and thinking of performance at large scales. When you build systems like Spark, MapReduce, you reason on data lakes and so on. So, we have this stack, we have done a lot of things. What happens is if you use a system, and maybe you'll experiment it when you use RumbleDB on the Azure cluster, sometimes it's going to be slow and you don't really know why. So why that can be, it could be that you're not using the right system. Maybe you're actually manipulating graphs and you're using a system that manipulates trees. So that makes it slower. It's an impedance mismatch. Sometimes, and very often, it's actually going to be what's called a bottleneck. A bottleneck means that in your system, it's made of plenty of parts that interact with each other and plenty of layers. And some parts are actually working quite well. They are not using all the resources, but some of the parts are going to constrain things and make things slower. So whenever it's slow, you have to go ahead and try to find where the bottleneck is, because this is where you should act on in order to make your whole system faster. But I have good news for you. Without being a hardware person, there's also people who know hardware much more than I do at ETH. The source of the bottleneck is almost guaranteed to be either the memory or the CPU or the disk input-output or the network input-output. Almost any time it's going to be one of the four. And it's going to be exactly one of the four, never two at the same time. For example, it might be that the CPU is going like crazy at 100%, but your memory is not used fully, the disk is a bit idle, the network is not using the full bandwidth, and so on. So in that case, there is a word, we say it's CPU bound. It basically means the CPU is completely overloaded. There's something wrong or that can be improved with the code. In another case, it might be the disk that is completely overloaded, right? The CPU is mostly idle, but you're just reading and reading and reading and reading and reading from the disk like crazy. This is where you should consider moving to a cluster, because that means you're limited by the computer you're using, or you should use more machines with more disks in parallel. You could be memory bound. Maybe it's your memory is completely full and it keeps swapping to disk and so on, right? So then you have a problem with the footprints of your data in memory, or it could be the network. You're overloading the network with shuffling all over the place. So shuffle is typically going to be the reason, and so on. It's exactly one of the four. So again, if the bottleneck is disk I/O, then you should automatically have the thought, okay, how do I solve disk I/O? Well, I can parallelize more and go to a cluster. In terms of measurements, whenever you want to identify the bottleneck, you might need to understand what's going on, what's the latency, what's the throughput, and so on. And again, we saw these prefixes that exist, right? Kilo, mega, giga, and so on. By the way, there are two more that were announced. I should add them to the slides as well now for 27 and 30. So it's Quetta, I think, and I can't remember. Does anybody know the 27th? Yes, I think Rome. Yes, Rona. Yes, Rona. Rona bytes and Quetta bytes. These are the two more. I will add them here as well. But it turns out you also have the ones for negative powers. So these are for the sizes especially. But this is very useful. The negative powers for nanoseconds and so on. Whenever you try to reason about times that it takes, right? You should at least know these four by heart. Milli, micro, nano, pi. Who knows them? Okay, you should. The other ones, maybe it's for physicists. We are less going to need them, but at least these four you have to know by heart. And here I included, and I will, again, that's for future reference. I will maybe change the color here. So I included a few numbers to show you the sort of things that happen on the hardware level and the order of magnitude that it has. So I'm just putting it for reference, right? So you have what's close to the cache is usually fast. When you read from memory, it's a bit slower. And when you ship data over the Atlantic Ocean, then it's even slower, right? So you just need to know roughly what is fast, what is slow with orders of magnitudes in your head. Then for the throughput, how fast can you send the data? You need to understand the speed of your network. Is it a 10 gigabit Ethernet or 100 gigabit? Are you writing to a hard drive or to an SSD? The SSDs are a bit faster, right? And you should know these orders of magnitudes. Like a few hundreds of megabytes per second is typically what you get from a hard drive. And knowing that, you can do some math on a napkin, right, in order to find out what in your system is not working. All right. So the total response time of your system is basically in the end going to be made of latency. You wait for something, you wait for the data to cross the Atlantic Ocean, and the transfer time, meaning that you actually transfer the data all over, right? And what's going to happen when you want to speed up a system is that you have the old response time and the new response time. Some people call latency the whole thing, right? So this is why you might see latency in that other meaning, that latency is just the total response time. So when you want to speed up, you just divide the old response time with the new response time. For example, it went from 3 seconds to 2 seconds, then you have a speed up of 1.5, right? So this is the napkin math that you can do. But what's important is that sometimes you're not going to improve the whole system. Maybe you're going to improve 30% of the system that is parallelizable, you're going to double the speed. But what is the impact on the whole system? Well, you have formulas for that. Somebody called Amdahl came up with a formula. So if you double the speed on only 30% of your system, the improvement is actually 18%, right? And you can use this formula for computing that. However, somebody else called Gustafsson has another formula. He says, no, that's how you should compute the speed up instead. So if you speed up, if you double the speed on 30% of your system, that is actually an improvement by 30%, right? So you got the whole 30%. So how is it that two different people are actually going to give you different formulas for the impact of the speed up on a system? And in fact, the difference has to do with the fact that Amdahl considers one problem that you need to solve. And then he asks the question, okay, how faster are you solving that same problem with your improvements? And this is where his formula comes from. Gustafsson is a pragmatic man. Gustafsson knows what happens when you start improving things. If you start making things faster, then people are going to use it more and solve even more problems. This is what's going to happen. So Gustafsson considers that the computing power is constant, and if you make things faster, you just do more things. So this is why if you improve a system, you're going to be solving more problems, right? So these are just two perspectives on things. Okay. Now I have some high-level remarks on the sort of things that you can tune, but a lot of that is repeated. How can you solve, disk I/O, for example, scale out? Just go on plenty of machines. Now you have 100 hard drives, so you have much more I/O. You can scale up. In some cases, you really cannot find any other solution, so you just add more memory. If you know that the bottleneck is the memory, because if you add more hardware on something that wasn't the bottleneck, it's totally useless, right? So you need to identify the bottleneck. Sometimes that's the last resort. You have no other choice than just add more hardware, more memory, faster CPU, and so on. But basically, you need to be very careful that this is based on the bottleneck you identified. If you want to avoid memory scale up, there are plenty of tricks. Try to write better code, right? You can find more efficient data structures in memory, right? Maybe a tree map will take less space than a hash map, for example. Do you have redundancy in memory? Are you storing several times the same things, right? Of course, redundancy can make things faster, but at the cost of more memory. So if now your bottleneck is the memory, maybe you want to remove the redundancy and then overload the CPU a bit more, since the CPU was more idle, right? Inheritance has a cost also in memory. If you use object-oriented programming and subclasses and so on, then that takes space as well, if you have sub-objects. Maybe in your code, and that's actually all over the place, plenty of places where that's the case, do you have unused fields? Maybe you have an object, a class that has fields that is created 1 billion times in your system, and there are 1 or 2 fields in there that nobody ever uses. Just remove them. You're going to have the size of these 2 fields times 1 billion. This is enormous, the gain that you can get from that. CPU scale up, there's also plenty of tricks in order to make things faster on your CPU, right? Maybe I should stop right here. I'll continue next time, but I'll give you a few tricks about how to solve the CPU bottlenecks that are kind of practical things. I'm going to stop here because I see it's 8:59. Next week, I'll finish this about a few tricks, tips and tricks on performance, and then we look at data cubes. and how to query data cubes. So thank you very much. And I'll see you next week for the last but one lecture. Thank you.